What specific problem does the information contrastive learning (ICON) framework aim to solve in the realm of representation learning?
The information contrastive learning (ICON) framework aims to address the complexity and diversity of loss functions in representation learning, which complicates the understanding of how different methods relate and which objectives are best suited for specific tasks. By introducing a unified information-theoretic objective, ICON integrates over 23 distinct representation learning techniques, including supervised, unsupervised, and self-supervised methods, under a single mathematical framework. This unification clarifies the structure of existing techniques and facilitates the transfer of ideas across traditionally separate domains. Additionally, ICON enables the derivation of new unsupervised loss functions that significantly improve performance on standard image classification benchmarks, thereby enhancing the overall effectiveness of representation learning methods. Ultimately, ICON seeks to simplify the landscape of representation learning by providing a coherent foundation for various algorithms and improving their performance through a generalized approach.
How does the proposed ICON framework work? Illustrate its step-by-step methodology, including the construction of supervisory and learned distributions.
The ICON framework operates by minimizing the average KL divergence between two conditional neighborhood distributions, which define transition probabilities between data points. First, it establishes a supervisory distribution, PJI, which is typically fixed and can be based on various criteria such as augmentations or class labels. Next, a learned distribution, Q_phi_Ji, is parameterized by a neural network and is optimized to align with the supervisory distribution. The optimization process involves adjusting Q_phi to minimize the KL divergence, D_KLP, Q, ensuring that the learned representation captures the underlying structure of the data. By varying the definitions of P and Q, ICON can unify various representation learning methods, including clustering, contrastive learning, and dimensionality reduction, under a single mathematical framework.
Can you provide a simple yet illustrative example that demonstrates how the ICON algorithm aligns the distributions and minimizes the KL divergence?
A simple illustrative example of how the ICON algorithm aligns distributions and minimizes the KL divergence can be seen in the case of stochastic neighbor embedding, SNE. In SNE, the supervisory distribution, PJI, is defined by placing a Gaussian around each high-dimensional point, x_i, representing the probability of selecting neighbors in the original space. The learned distribution, Q_phi_Ji, is similarly defined by placing a Gaussian around the low-dimensional representation, phi_i. By minimizing the average KL divergence between these two distributions, ICON ensures that points that are close in the original high-dimensional space remain close in the embedded low-dimensional space, effectively preserving local structure. This process illustrates how ICON can unify different methods by aligning their respective distributions through a common objective, thereby enhancing representation learning.
What are the practical advantages of using the ICON framework compared to existing methods in representation learning, particularly in terms of performance on benchmarks?
The ICON framework offers several practical advantages over existing methods in representation learning, particularly in terms of performance on benchmarks. Firstly, it unifies over 23 distinct representation learning techniques under a single information-theoretic objective, which clarifies the relationships between various methods and facilitates the transfer of ideas across different domains. This unification allows for the derivation of new unsupervised loss functions that significantly outperform previous methods, as evidenced by an 8% improvement in unsupervised ImageNet 1K accuracy and additional gains on CIFAR 100 and STL 10. Secondly, ICON's self-balancing loss function eliminates the need for manual tuning of regularization parameters, leading to more robust and accurate clustering results. Lastly, the framework's ability to incorporate insights from contrastive learning into clustering methods enhances performance on complex datasets, demonstrating its effectiveness in improving existing methodologies.
How was the ICON method validated in your experiments? Please describe the experimental setup, metrics used for performance evaluation, and any benchmarks against which it was compared.
The ICON method was validated through experiments on the ImageNet 1K dataset, which consists of over 1 million high-resolution images across 1,000 classes, making it a challenging benchmark for unsupervised image classification. The primary metric for performance evaluation was Hungarian accuracy, which measures the quality of cluster assignments by finding the optimal alignment between predicted clusters and ground truth labels using the Hungarian algorithm. The experimental setup involved training various Dino pre-trained vision transformer (VIT) models, VIT-S14, VIT-B14, and VIT-L14 for 30 epochs, utilizing a batch size of 4096 and applying data augmentation techniques to enhance feature representations. ICON was compared against several state-of-the-art clustering methods, including TEMI, SCAN, IIC, and contrastive clustering, demonstrating significant performance gains of +4, 5%, and +7, 8% in Hungarian accuracy for the VIT-B14 and VIT-L14 models, respectively. This validation underscored ICON's effectiveness in improving clustering performance without the need for additional regularization, hyperparameter tuning.
What limitations or potential drawbacks did you observe with the ICON framework, especially concerning its application across different domains or tasks?
The ICON framework, while unifying various representation learning methods, does have limitations, particularly in its application across different domains. One potential drawback is the challenge of ensuring that the supervisory distribution, PJI, remains valid when incorporating additional uncertainty, as modifying it can complicate its extension to clustering or supervised tasks. Additionally, while the framework allows for the transfer of techniques between domains, the effectiveness of these transfers may vary, as evidenced by the sensitivity of performance to the debiasing parameter, alpha, and neighbor propagation strategies, which require careful tuning for optimal results. Furthermore, the reliance on specific choices for neighborhood distributions may limit the generalizability of the framework to all types of data or tasks, as not all datasets may benefit equally from the same configurations. Lastly, the empirical results suggest that while ICON improves performance, the gains may not be uniform across all model sizes, indicating that larger models might require more nuanced adjustments compared to smaller ones.